Thank you, Ann. And just to provide a little bit of additional context, I grew up in a 1710 home in Pennsylvania, actually, a log home made of chestnut logs. And I currently live in Dummerston. I've lived for 30 years in a home built in 1788, roughly, with an addition put on around 1800. So I've always had an appreciation of our heritage and the architecture that our forefathers provided for us. And we recently, my wife and I, bought a farm close by, and we're about to embark on restoring both a barn and a house. So we're deep into that, and really excited to get some new experiences with that, and also create a working farm in the process on a place that had a farm 50 years ago. So thank you for coming this afternoon. I'm going to talk about resilience and resilient design, really addressing work that I started following Hurricane Katrina. Our company is in Brattleboro BuildingGreen, which focuses on sustainable building practices. And when Hurricane Katrina struck in the Gulf Coast, a number of us, actually organized by a group in St. Louis, organized an effort by the U.S. Green Building Council to do what we could to make the reconstruction that was going to happen more environmentally responsible. They got me involved. I worked with them in a number of different charrettes looking at reconstruction in the Gulf Coast, recognizing that even though some areas arguably should not be redeveloped due to flood risk, they were going to be redeveloped. So, how could we make them less vulnerable in the future and more sustainable? And in that process, we observed that, as many of you know from watching news back then, residents in New Orleans were evacuated to the Superdome, and then shortly thereafter had to evacuate the Superdome because it was 105, 110 degrees. It was a building that, wasn't designed to be without electricity, and the city was without electricity for several months. At the same time, the older homes that were not flooded in New Orleans, in the French Quarter area, those that were older homes built, say, in the early 1900s and earlier, were basically fine. They didn't have electricity, but they were livable. They weren't exceeding safe temperatures in those buildings. They were designed with vernacular architecture, wraparound porches that shaded the windows from direct sun, tall ceilings, ventilation design that allowed air to flow through the buildings, just smart architecture that was designed, that was based on that part of the country. So we thought about that, and in the reconstruction that was going to happen, what could we do to encourage that the new houses and the reconstructed houses would be able to withstand the next event? And the one thing we knew with certainty was that that wasn't going to be the last power outage in the Gulf Coast. So out of that effort emerged a concept we initially referred to as passive survivability, creating a home or school or commercial building that will maintain livable conditions in the event of loss of power, loss of heating fuel, even shortages of water. I've since been talking about that more under the rubric of resilience, which is a more friendly term. It doesn't scare people off quite as much, but the concept is basically the same. So that's what I'm going to talk about a little bit here. How can we create buildings that will not only do better in whatever the event is that's going to happen, but also in the aftermath of the event. And a lot of the focus of FEMA and for all the great work they do, a lot of that focus tends to be on how to create buildings that will survive the storm event or the flooding or the fire or the earthquake or what have you, and not how that building will behave in the possibility of being without electricity for an extended period of time, or being cut off from heating fuel, or even communities that get cut off from access to services. So I'm going to go through that a little bit. Just to start with, this photo that you're looking at here is a really interesting home in Ann Arbor, Michigan. It's a home built, I think it was in the early 1900s, but they did a deep energy retrofit of it, turning it into a net zero energy home. So basically self-powered all of its energy consumption. And they did a quite good job in dealing with the architectural characteristics of the house. One can argue that a photovoltaic array doesn't belong on a historic house. I tend to think it does, but they did that, and they chose specifically a dark panel, not a blue panel, but a fairly black panel to minimize the sort of aesthetic objections that might occur with that in a historic district. Okay, so why are we talking about resilience? There are a lot of reasons, and Peter Shumlin alluded to some of those at our keynote this afternoon, having to do with climate change. We're going to see warmer temperatures. What can we do to create buildings that will do well with warmer temperatures, without needing to rely on increased air conditioning and consumption of electricity? There's some scary numbers out there and scary graphs. These ones on the right show the recent past, the temperatures, and then what might happen with different scenarios of continued carbon dioxide emissions, much higher temperatures. The deep red colors in those maps are temperatures of over 110. The darker colors are hotter temperatures. So pretty dramatic change. So that's one of the factors we want to consider. We need to be designing for more intense storms. And this isn't only about the future. We can look back at the data from the past 50 years and see that there's been a pretty dramatic increase in the Northeast in intense weather events. More precipitation happening in shorter duration episodes. In the Northeast, a 67% increase over the last 50 years in what they call intense storm events, defined as the heaviest 1% of all events. So that's something we need to be thinking about in designing both new buildings and retrofitting or remodeling or restoring older buildings. And we, of course, saw that here vividly last year. It's not only rain events, but ice events as well. Some of you may remember in January 1998, there was an intense ice storm throughout much of eastern Canada and northern New England. Deposited 3 to 4 inches of ice over a 5-day period. It was enough ice to crumple large power distribution towers, such as the one on the left there. I think it took down 130 of those and some 30,000 more standard utility poles. It left vast areas of eastern Canada without electricity for 3 weeks anyway, some places even longer than 3 weeks. Most places had fuel, but they didn't have a way to use that fuel. So houses had to be abandoned basically until power came back. 99% of our fossil fuel heating systems require AC electricity to operate. So if we don't have a backup generator, we don't have access to that heating equipment. So many people had to relocate for fairly extended periods of time. Drought is another issue. One of the overall impact of climate change is expected to be an increase in precipitation globally. Warmer temperatures will evaporate more moisture from oceans and lakes. So there'll be more moisture in the sky, raining down, so higher precipitation levels. But the climate scientists predict that there will be changing precipitation patterns. So some areas get a lot more rain, and significant areas get a lot less rain. And much of the western United States is predicted to have significant drought conditions over the next 50 to 100 years. In fact, there's relatively new data showing that the period of the last 100 years with relatively plentiful rainfall in the western U.S. was an anomaly, an historic anomaly, and more typical is much less rainfall. And that's significant because the allocations from the Colorado River, which is the lifeblood of a lot of the western U.S., those allocations were developed back in the early 1900s at a time of fairly plentiful rainfall. And the prediction is that the actual average, let alone climate change, but the actual average from past performance is much lower flows of the Colorado River. That'll have huge impacts. There's a great resource that some of you might have come across, the U.S. Drought Monitor, run by the University of Nebraska in Lincoln, where you can go on that website and look at their drought maps on a weekly basis. The larger map on the right was earlier this week, June 5th, showing drought conditions around the country. And then I've got about a year ago on the lower left. And you can see how much the variation is from year to year, even month to month. And actually, this time last year, I was on a bicycle trip through the Southwest, and most of the area I biked through hadn't seen a drop of rain since the previous October. So dramatic drought last year in the South, Texas, Arizona, New Mexico. This year, there have been some areas of growing concern in the Southeast, which is significant. The Southeast isn't used to drought. It's not something they've grown up with. In the West, we kind of expect drought every decade or two, significant drought, and we've learned to conserve water. In the Southeast, not only are we not used to doing that and curtailing our water use, but the reservoirs upon which we depend for water tend to be much shallower. In the West, we have very deep reservoirs like Lake Mead that hold, years worth of consumption. In 2007, when there was a significant drought in the Southeast, Lake Lanier, which is pictured here on the right, and from which Atlanta gets most of its water, nearly went dry. They were within 30 days of running out of water, not just needing to curtail water, but actually running out, with really no plan in place of what to do about it. The governor, some of you might remember, urged residents of the state to participate in prayer vigils to encourage the gods to offer rain again. And I suppose that worked because rain did eventually get them out of that bind. But we're seeing, this year, as shown in that last slide, some areas of significant drought concern that are emerging again. One of the reasons this is significant, it's not only about water, it's also about electricity. Roughly 89% of power production in the U.S. comes from thermoelectric power plants. These are power plants that use some kind of heat source, whether it's coal or natural gas or nuclear fission, to generate heat, which boils water under very high pressure, generates steam, and then they need significant, huge quantities of water to cool that steam, condensing it back into water. More modern plants recycle the water, so there's relatively low loss. Older plants use it once through, returning it back to the water source from which it was drawn. In 2007 in the Southeast, there was one nuclear power plant, a Tennessee Valley Authority plant, that had to shut down because for lack of cooling water, and there were another 20-some nuclear plants in that region that were threatened with either curtailed power or actual shutdown. In a more significant drought and heat wave condition in Europe in 2003, there were several dozen power plants that either had to shut down or go into reduced output at a very difficult time, because it was a You know, a severe heat wave, the worst heat wave on record. Over 30,000 people died in that, centered in France, but in a lot of Western Europe. And you know, that's just when you don't want you know, to have to deal with brownouts and rolling blackouts due to inadequate power production. So this is something we need to think about with drought. You know, whether our electricity supplies are vulnerable to that, or whether we can rely on those. And that's something I'll talk about as we go along here. Wildfires aren't a big issue in this area. In my bicycle trip through the Southwest, I was having to dodge wildfires in West Texas. You might have seen news stories about that. This was an area I rode through where there's hundreds of square miles that had just burned the previous week, and I had to delay my departure and shift my route a little bit to deal with that. You know, fortunately, we're not dealing with that in this part of the country, although in an exceptional drought, that could change. So it's something to be conscious of. And then there's the issue of you know, the non-natural disasters, but vulnerability of our power generation systems and power distribution systems, specifically the electric grid, oil refineries, oil pipelines, gas pipelines, and so forth. You know, we have 3,400 power plants in this country. Each of those is a point of vulnerability, and you know, the Department of Homeland Security is very concerned about this and doing studies, doing tests of the vulnerability to terrorism, both old-fashioned terrorism and also cyber terrorism. And there was an interesting study, test that was done a few years ago at Idaho National Laboratory, where they actually hacked into a control system for a generator, and they were able to, you know, sort of force that generation system to operate out of phase and self-destruct. You know, and there's a video, YouTube video you can find online that was declassified by the Department of Homeland Security, where you can see this generator start vibrating and little puffs of smoke come out, and it then shudders, and finally it just masses of smoke coming out of it as it was destroyed. And you know, this level of sophistication with hacking was demonstrated with the efforts in Iran that I'm sure a lot of you read about, where our intelligence agency were able to hack into the control systems of breeder reactors or the nuclear industry development capability in Iran. So that's a concern, you know, that some you know, groups could hack into the control systems and knock out power to significant parts of the country. So just another point of vulnerability. Okay, so given these points of vulnerability, whether it's through climate change or unpredictable natural disasters like the Fukushima earthquake and tidal wave, tsunami that happened, or whether it's more you know, evil intent terrorism, there's concern. And what can we do about that in strengthening both our buildings and our communities? So I'm going to go through sort of a quick tour of some of these, and then hope to have plenty of time for discussion afterwards. So first I'll start with flood resistance, certainly top on our mind, particularly in Wilmington and Brattleboro, where we're based. This is downtown Brattleboro, Flat Street, during that Irene flood. And the Flat Street, basically the Whetstone Brook jumped its bank and flowed down Flat Street. There were cars floating down the street, propane tanks, and so forth. Nearby, and Joseph Sincata mentioned this in a presentation just a little while ago, the New England Youth Theater is kind of a really neat story for resilience. You can see the flooding, it's the building, you can see the marquee over on the left of the New England Youth Theater. The architect and engineer, Bob Stevens, who's here with us this afternoon, Looked at that. The building was above the 100-year flood zone by about a foot, so they didn't have to do anything, but they wanted to create a building that was going to be more resilient, so they went beyond the requirements and added these flood barriers. And you can see on the right, Jerry Stockman tightening turnbuckles on these floodgates that are installed on the interior side of the entry doors. They were 20-inch floodgates. The water came up to within an inch of the top of those. Without those floodgates, the building would quite possibly have been a total loss. As it was, there was a little bit of carpet damage, I think $5,000 worth, but very minimal damage, very easy to repair. And these literally saved the building, which had only been completed a couple of years earlier. So a great success story and a demonstration of a little bit of forethought in the design and a client that's willing to keep features like that into buildings rather than value engineering them out. There's often pressure when push comes to shove. You've got to save money in the bottom line. These floodgates aren't required. They were, I don't know how much, a few $1,000s extra. It could easily have been cut from the specification, but they kept it in, and they're certainly glad they did. I should mention before I go there, with other things that can be done relative to flood resistance. Those who were in the session with Joseph Sincata a few minutes ago, he talked about a project he's doing right over here in downtown Wilmington, trying to create an interior space that has flooded in the past, flooded with Irene, and will flood again. How to make that a space that will survive flooding, where you don't have to rip out materials and get rid of them. So that's an important part of it as well, specifying wettable materials, wettable and dryable materials. Drywall, if it gets wet, it's out of there. You can't really recover it because of the mold risk and damage that's irreparable. A lot of cellulosic materials, same thing. But polished concrete is a great flooring system. That's what they've used in the Brattleboro Food Co-op that's nearing completion in Brattleboro. The flooring on that whole floor is polished concrete. There would be zero damage to the floor with flooding. Merchandise, of course, is a different story. But there are decisions we can make like that, that ensure greater survivability of those building materials. In the reconstruction, this flood-proofing of buildings, it goes much beyond the building scale to the community scale. And the state of Vermont, when they were replacing culverts that were washed out in Irene, such as this one, instead of putting back a single culvert, they either put back larger culverts or multiple culverts, so that the next storm event, that culvert system is going to be more likely to carry those elevated storm flows. It's when you fill up that culvert or it gets a single culvert gets blocked, that's when you wash away the road system. So again, some forethought. It's more expensive, but will save a great deal of money down the road with the next storm event. Designing for extreme wind is an increasing priority. Climate scientists tell us that we will be seeing more intense storm events, not only more precipitation, but greater wind. That's partly driven by rising water temperatures in the South Atlantic and Gulf Coast that add more energy to tropical storm systems. So the prediction is that hurricanes on the East Coast will be more severe over the coming decades than they have been in the past. So, I've been recommending that people build throughout most of the country, certainly all of the East Coast, to the strictest hurricane codes in the country, the Miami-Dade County codes. Not that they have to follow the letter of the law for that particular code, but to, provide tie-down strapping and, well-established techniques to keep roofs from blowing off and shingles from detaching. So just pretty much a lot of these ideas are common sense, but you know, until the building codes catch up to reality, you know, we need to use that common sense to actually do these things. This just shows the extreme wind conditions map. These are driven largely by tornado occurrences in the red and yellow. The checked area along the Gulf Coast and Atlantic coast is hurricane risk. Just shows these are FEMA zones for designed for high energy wind. We talked a little bit about fire earlier. While we don't have to worry about wildfires as much in New England, we certainly have to worry about fires. This is Brooks House in Brattleboro, which suffered a devastating fire May a year ago. The fire itself wasn't really so bad. The building was sprinklered, the fire was extinguished, a great fire department put it out, but the water damage did phenomenal damage, you know, millions of dollars worth of damage. That's Bob Stevens on the right, who is putting a team together to purchase that building and put it back into use. Certainly hoping he succeeds with that. It's a really exciting project. It's a challenging one, but you know, we really need it in downtown Brattleboro, and I think he's going to succeed with it. But I got an opportunity to tour the building when the immediate repairs were being done. It was really neat to see the bones of that building. They had wisely pulled off all of the interior finish before the mold set in and were able to dry out the building so that this will be able to be rebuilt. And not only rebuilt, but there's an opportunity, sort of a once in a building lifetime opportunity to really address the fundamental envelope systems in that building and beef up the energy performance. You know, you could never economically justify taking a building like this up to today's recommended levels for insulation, for example, unless you have to do something extreme like this, where you're having to pull off the entire inner surface of that building. So they're looking at significant upgrading of the energy performance of the envelope, and you know, I've certainly been urging them to do that from the perimeter. So it's a neat project. I think I've got another slide a little bit later about that. Oh, here's one. This is the roof area, which did have to be replaced. This is about to put a new roof on that was prefabricated on the ground and lifted into place by a large crane. But it's an amazing building for those of you who haven't seen it. I think there were 49 apartments in the upper floors and 11 businesses in the ground floor, all of which disappeared. One of which was Bartleby's Books, the bookseller in Brattleboro. So they had the double hit with the fire at the Brooks House and followed by the Irene flood.
Is this building near the downtown?
Yes, this is really most of the main block between Elliott Street and High Street on Main Street. It's that whole corner that, you know, all shuttered businesses today, but hopefully to come back. And it's possible that the, which is the college that may come in there, Bob?
CCD.
Yeah, Community College of Vermont is looking at that space as a possible Brattleboro campus. So that would be a sort of an anchor tenant, and I think make the financing more viable for this whole project. Okay, so then I'm going to spend a little bit of time talking about energy performance. You know, that's sort of my shtick. I've been promoting energy conservation for 30-some years now, and when I look at resilience, it's not only about the storm or the flood or the fire or the earthquake, but it's about how that building will do if it loses power or loses heating fuel, you know, as can happen with many types of events, as we talked about. And you know, the goal, in my mind, with resilient design is to create a building envelope that you could basically turn off the energy inputs, the electricity or natural gas or propane or heating oil, and basically have that building coast, maintaining safe, relatively livable conditions. You know, you might have to wear a coat if you're in there, but it, you know, with enough insulation and some passive solar gain, that building won't drop below about 50 degrees. You know, it's never going to risk freezing. You know, it provides a level of resilience that I think makes a great deal of sense. Relatively easy to do that with new construction. You know, and by building homes with our 40 to 50 walls, our 50 to 60 ceilings, triple glazed windows that are R5 unit value. You know, those levels of performance achieve, you know, that type of resilience where that building will never go below freezing or even approach freezing. With existing buildings, the challenges are far greater, and I think all of you in this room are well aware of that. But there are things that can be done. It's hard, but it's hard and it's expensive, but it can be done and should be done whenever we have that opportunity. This photo on the right shows a passive house retrofit of an 1880s brownstone in Brooklyn, New York. Passive house is a rating system for ultra-low energy consumption homes. It came out of Germany, the Passive House Institute. It's really caught on around the world. There's an active community in the US that's pursuing passive house construction. This was one of the first renovations to create a home that met the passive house standard. So they took this old brownstone and, you know, pretty dramatically upgraded the envelope and the windows to achieve that performance, and they did so within historic codes in that part of Brooklyn. The photo on the left, it's a little hard to see, but they used a combination of systems in the walls to, you know, both cellulose insulation and rigid foam to provide much higher R values in the walls. There are a lot that can be done. There are many different solutions for insulating. The photo on the right is a project in Colorado, another historic retrofit, the Chicago Chautauqua. From the late 1800s it started, and there are about 50 cottages that a nonprofit there is gradually upgrading, and they still use them for the original idea of a Chautauqua, which was bringing people in for kind of intensive learning environments. And Jeff Medanich is doing that work, and they're, you know, in this case, they took the original, they went down to the studs, furred them out to get additional depth, insulated with rigid foam to the sheathing, and then added some additional insulation to the interior of that, creating a very good air barrier and insulation levels. Very different approach. This is in a home outside Boston. It's a 1920s Sears Roebuck or 1916 Sears Roebuck kit home, so-called a Foursquare Home, where they did what's often called a deep energy retrofit. They went through the house, and on most of the house they did outboard insulation, adding 4 inches of rigid foam to the exterior. The home had a good overhang already, so they were in good shape that way. They could add 4 inches and not compromise drainage too much. But then in dormers and some of the interior attic space where they were creating living space from what had been unheated space, they used spray polyurethane foam. This is an open cell foam called Isoline. So they got very good performance. You know, this is a photo of putting siding on over the rigid insulation that was installed on the exterior. You can see in this home something that Joseph was talking about in the last session, the Rainscreen Detailing, which I think is critically important. I think it should be building code in most of the country, but basically providing an airspace behind the siding. This not only allows the space to dry out between rain events and to allow that siding to dry out from the back as well as the front, but it blocks the capillary flow of moisture through that wall system. It's a capillary break. So it makes a great deal of sense with a good Rainscreen detail and back primed siding. You should go 15 years between painting the siding, wood siding on a home. So it just makes so much sense that we shouldn't think about not incorporating Rainscreen detailing whenever we have the chance. This is another photo of the Brookes house showing a detail of the exposed wall system. It's a little hard to see here, but you can see they took off all of the interior finish material, exposing the original structural brick. It's a 3-weight brick, so it's a pretty thick masonry wall system, and you can see wood siding above that. So there's a significant space there that could be filled with a spray fiberglass or a spray mineral wool, which would have moisture control properties, and then rigid insulation could be added to the interior to achieve an R40 target, which I think would be great if they can achieve that in this building. This is a building in Brattleboro, my colleague Peter Yost's home. It's a home, I'm not sure when it was built, in the 40s maybe, but it had this kind of odd concrete masonry unit construction on the exterior, horribly insulated, very high energy consumption. He basically did a deep energy retrofit over a number of years, adding exterior insulation. He had enough of an overhang to be able to do that and still get drainage off the roof. And he's done a lot of other things that we can talk about with windows and so forth. But one of the really interesting things he did, because he was losing overhang space in furring out the wall, he basically installed a detail that Bill Rose at the University of Illinois has pioneered, which he refers to as the underground roof. Basically at ground level, providing an impervious barrier that will carry moisture away from the building. So that rain will splatter down in there and percolate through a pervious surface above crushed stone, for example, but then carry it away from the building, helping to reduce the moisture pressure coming in toward the basement. He refers to it as an underground roof. Yes?
Why wouldn't it run all the way to the foundation?
Pardon?
Why would that not run all the way to the foundation?
That's a good question. He just sent me these photos, and I'm going to ask him the same thing. I'm doing this at my house right now and plan to go right to the foundation. I did it before, and it didn't quite work because moisture got in at some window wells. And in my case, I'm going to eliminate those windows into the basement on the eave sides of the home. So I'll eliminate 4 windows, leaving the gable end windows, but controlling the moisture. And in my case, I used an EPDM barrier, a EPDM rubber. I also added insulation to provide insulation of that dry stone foundation. Those rubble foundations typically have a vertical interior wall, and then the exterior kind of tapers away from the building. And so I put on sloped insulation. This was 30 years ago. Used extruded polystyrene to try to insulate that foundation as well as I could, without destroying the view of the stone from the interior. It's a gorgeous foundation system that I didn't want to lose. Yes.
Earlier in the talk, and it goes back to a few other slides, in terms of building materials that are more resistant towards flooding.
Yes.
And in terms of insulation, what are they?
Yeah, the question is in terms of water-resistant insulation materials or water-resistant materials, what are the options with insulation? Yeah, it's a good question. Extruded polystyrene has for years been the product of choice for moisture environments, wet environments. In fact, it's used in the inverted roof membrane assembly or IRMA roof in commercial buildings, a flat roof where the membrane gets laid down, the roof membrane, and then the insulation on top of that. So the insulation stays wet a lot of the time, and extruded polystyrene performs quite well in that situation. There are other materials that I like better than extruded polystyrene. Extruded polystyrene has a couple of environmental problems that I've written about in our newsletter, Environmental Building News. You know, one of which is the global warming potential from the blowing agents that's used in XPS. The other is the flame retardants that are used. There's a brominated flame retardant that's now being banned in Europe called HBCD that's used in all polystyrene insulation. So I'm actually in the house we're about to renovate planning to use a product called foam glass. It's a cellular glass product that's been made by Pittsburgh Corning since the 1930s. It's a very high temperature, totally moisture impervious material, totally termite resistant. It's the most insect resistant insulation material out there. While extruded polystyrene does very well from a moisture standpoint, termites can eat right through it. Foam glass is very resistant to, or totally resistant to insects. In fact, it's often used as an insect brake in commercial building assemblies. But I'm planning to use that for both beneath the slab, that we're pouring a new slab and foundation walls, both beneath the slab and on the outside of the foundation. Very good material from a environmental standpoint and a moisture standpoint. It is expensive, which is unfortunate. Yes, sir.
What about metal?
I'm sorry?
What about metal? Using metal sheets?
Metal sheets. Well, in a moisture contact situation, there'll be rusting involved or damage to the metal over time. And if you're talking about insulation, it would be a metal sheathing on some kind of insulation, and metal polyisocyanurate panels exist. They're not that common in residential construction, certainly more common in commercial construction, but not used below grade typically. Polyisocyanurate isn't a good insulation material for below grade applications because it can absorb water over time. It can be used, but it requires really careful moisture detailing to keep it from being in moisture contact. In the back.
Yeah, I'm very familiar with Victorian houses that have a concrete pad that comes all the way around the house and slopes out. We used to play there. Why didn't you consider that?
Yeah, the question about a concrete skirt. I think that's a pretty good idea. It means mixing up concrete. What I used at my place was an aggregate, clean crushed stone skirt, and then the drainage beneath it. But concrete can work very well in addition. There's the point of contact between the concrete and the house, which you need to still deal with. With an EPDM layer, you can put it up above the lower layers of clapboard and have it extend down on top of an insulation layer, for example. But there are a lot of ways to skin the cat. Yeah.
Wouldn't frost with concrete fingers in that insulation? If you insulated the outside walls, you would.
Yeah. Good point. Yeah, frost heaving could be an issue with concrete, a brittle material like that. Yeah.
That glass cell that you speak of, is that a loose fill process?
Well, foam glass, it's primarily sold as a rigid board stock, and it's, you know, you might have seen it. It's often sold in chunks as a sanding block, and it's used in certain applications. It's got sharp edges from the, you know, it's a very fine millimeter scale cells of glass, so it can work in sanding. And if you've seen it and you scratch it with your fingernail, it has a hydrogen sulfide smell because there's a little bit of hydrogen sulfide in the manufacturing of it, in the way they produce it using a sulfur process. Hydrogen sulfide isn't a gas that we like to breathe a lot of. It's the rotten egg smell. It's not good for us. But I'm very confident that, you know, the vast majority, you know, 99.999% of it stays in that cellular structure. They recently did a renovation of the Museum of Modern Art. No, I think it was the Guggenheim Museum, and it had been insulated with foam glass 30 or 40 years earlier, and they took some of it out, and you could still scratch it and smell that same hydrogen sulfide from just the outer millimeter or two of the layer. So most of that hydrogen sulfide stays in the insulation. The product is also available as a loose fill in Europe, and I gather that there are some suppliers that are beginning to provide it as an aggregate insulating fill in this country as well. So in other words, it could be used underneath a slab. You would lay down several inches of this, you know, spread it out smooth, and then pour concrete on top of it, and it would, you know, serve not only as a drainage layer but as an insulating layer. So it could, they're both options. Yeah.
How about SIP panels as far as water resistance?
Structural insulated panels and water resistance, it's all about the installation. There have been some big problems with SIP panels that weren't properly installed in terms of sealing the joints between those panels. It's absolutely critical. Years ago, back in the 80s, I did technical literature for Winter Panel Corporation in Brattleboro, and worked on their installation manual, and, you know, spent a lot of time looking into the correct way to install those. And it's absolutely critical to get a very good continuous seal at those panel joints. And there are different ways to do that. Some panel manufacturers leave a channel that you come in afterwards and drill into it and inject spray foam to basically fill up that key, essentially, to lock the two panels together. There are other systems where you basically lay a bead of expanding foam sealant down and then shove the panels together, again with the little key joint between them. That's fine as long as you don't have to pull it apart again and jimmying the panels to get them exactly square and set properly. So it's very important. There have been some big lawsuits involved with SIP panel installations, I think most prominently in Alaska, where if you have air leakage through a roof panel, you're really going to know it. And, you know, they had extensive damage to roofs, and in a poorly installed SIP roof, you can see the seams every 4 feet or 8 feet where there's been swelling of the sheathing, where water vapor and air has leaked through from the interior and swollen the surface of the oriented strand board on the exterior of that. So they can be used, but you've got to do it right. Let me continue with these slides, and then I think we'll still have time for more questions. So windows and glazings, a big challenge in historic buildings. In new construction, you know, I argue for triple glazed windows with double low-E coatings and very tight construction. In the passive house community, the European windows are most popular, that have a pretty thick spacing between the panes of glass, triple glazed, 1 or sometimes 2 low emissivity coatings, argon gas fill, typically sometimes even krypton, a lower conductivity gas that conducts less heat through from the interior. But in historic buildings, that's often not easy to do with historic codes. So what can you do? This is Debevoise Hall at the Vermont Law School in Vermont. And what they did, there was a pretty extensive restoration of this building. They took the existing windows and added an interior fiberglass framed insulated glass window to the interior of that. So that was a low-E window. So they ended up with triple glazed performance with a modern tight window on the interior. So it's looser on the exterior, which is good if you've got a non-sealed system, so that any moisture that does end up between the layers of glass can escape. But then they've got this tight window on the interior and the operability and so forth. So that's been working very well as far as I know. It's one option. Storm windows can also go on the exterior. On the exterior, you can get a benefit of protecting the original windows better from UV light, depending on the glazing that's used. But it's something that often has to be negotiated with the historic code that's applies to that particular area. There was a project, this on the left here, the Brooklyn brownstone passive house that they did. They used German windows. I think they were German. They were European Optowin windows, and they had them custom made. Budget wasn't a big issue on this project, apparently, but they had them custom made to satisfy the historic code in that part of Brooklyn. But as with a lot of European windows, they're an inward opening casement known as a tilt-turn. So you can open them as a side-hinged casement by turning the handle one way, or you can turn the handle up when the window's closed, and then open it down so the top comes out bottom hinged. A really nice product. That mechanism sucks the window very tightly to the frame, so tilt-turn windows tend to have about the best air tightness performance of any windows. Really good system. The mechanisms are more expensive. They have to be heavier duty. The European windows tend to be thicker, so they need that beefier hardware. But that's certainly an option if the budget permits it and if the historic codes allow it. But with existing buildings in general, it's hard to justify the cost of window replacement over adding storm windows. And I've been trying to interest the window industry in developing some insulated storm windows. So 2 layers of glass with low-E as a storm window system. And they aren't unheard of, but I don't know of any off-the-shelf products that do that. Benson Woodworking in Brattleboro, right in the same SD Oregon complex where our office is located, has made these for a number of projects. And they're working very well. I think they used them in the Whitingham Meeting House. Very tall windows, even taller than these, with a round top. And they built these custom-made exterior storms that are gorgeous, that actually are insulating glass. So very good energy performance, and not eliminating the original glass, which, like this, is very appealing with the hand-blown texture to the glass. Cooling load avoidance is another very important resilience strategy. If we do find ourselves without electricity, we need measures to keep that building from getting too hot. And to find out how to do that, what you need to do is look at the historic buildings in the Southeast, where they were designed and built before air conditioning existed, and they provided reasonably comfortable conditions. So this house in Tupelo, Mississippi shows a wraparound porch, that keeps the direct sun out of the windows on the lower level. It's outside living space, so in the afternoons and evenings you can be outside where there's a breeze. high ceilings on the lower level, the ability to put in fans, slow-moving fans to move air, just smart design, vernacular architecture that was suited to that climate. It's not a system that you'd see in New England, but with climate change, we need to be more concerned about air conditioning in this part of the country than we used to be. In fact, more new houses are going in with central air conditioning than those that aren't having central air conditioning, even in Vermont. So air conditioning is becoming ubiquitous throughout the country, and we shouldn't turn our back on the common sense vernacular designs that enable us to do okay without air conditioning. Sun tempering or passive solar design is an important element. Even with the best envelope, if there aren't windows that'll bring in some solar gain and a mechanism to store some of that heat, the temperature in the home or commercial building will gradually drop toward the outside ambient average temperature. But with some smart solar design, south-facing windows with relatively high solar heat gain coefficient glass, glass that lets in a fair amount of the sunlight, we should be able to maintain much more comfortable conditions in the event of a power outage where we can't use our heating systems or a shortage of heating fuel for some reason. This is the south facade of the Gilman Ordway building at the Woods Hole Research Station in Falmouth, Massachusetts. It's a neat project. They took a historic house and turned it into a research laboratory, so a pretty significant change in use, but they were able to maintain a lot of the original appearance of the house facade. I think did a great job at it. Daylighting is another important strategy. This is particularly important in schools and other public spaces that may need to serve as emergency shelters or spaces that people will come to in the event of a community crisis of some sort, extended power outage or ice storm or situation where there might be a fuel shortage. Schools are typically the places of refuge or the emergency shelters in a community. So we should be designing spaces like this with good daylighting so that at least during the daytime hours, you're not having to run generators, using up critical diesel or propane fuel supplies to provide lighting for those spaces. And daylighting is becoming more and more common in schools, thankfully. And there are some really exciting studies that are showing better productivity among students, faster learning, better performance on tests, better teaching in schools with natural daylighting, and views to the outdoors, that bring the outdoors in. So there are some real benefits to daylighting, something we should be paying attention to. Pictured here was a photo I took out at Taliesin West, the Frank Lloyd Wright Architecture School outside Phoenix. Just a really neat use of daylighting in a classroom space. Water is another very important issue with resilience. In rural areas that don't have municipal water supply, well water is often the biggest inconvenience when we have power outages. Most of us have wood stoves and can keep our homes reasonably comfortable, but water becomes the limited factor and is what pushes more and more people to go out and buy generators. And generators, play a very important role, but I will say we learned with Hurricane Katrina that in a severe crisis where there's a, sort of a system-wide collapse of infrastructure, most of those generators stop working after about 24 hours. Either they run out of fuel, or the fuel has been sitting in a tank and gone bad over time, or the generators themselves break down because they're not designed for continuous use. So when we can become less dependent on generators and provide other mechanisms to provide electricity or systems for using less water or storing water, will be ahead of the game. So the starting point is to use less. You know, as with energy, we want to start by reducing consumption before we look at how to supply it with renewable energy systems. But with water, we want to cut our water consumption, and that means low flow fixtures, whether it's shower heads, faucets, toilets, dishwashers, clothes washers. We can go further if we want to with things like composting toilets, which work even when the sewage systems fail. You know, it's an interesting level of resilience. Outdoor consumption. This was a photo. I couldn't resist taking this when I was on my bicycle trip, showing lawns in an area of Phoenix where there's, if you can't see that, it's different colored stone. There's a green stone lawn in the foreground and a red stone lawn next to it. Quite inventive, I thought. Not my choice, but I wouldn't live in Phoenix for many reasons, including water. I should also say that I was astounded biking through there. I passed this development that had you know, dockside condominiums, you know, where everyone had their boats. There was this huge water system, all Colorado River water, but I thought I was in Florida all of a sudden with you know, every condo having its own little dock and motorboat out there. Just boggled my mind that that exists in a place with as high an evaporation rate as Phoenix. We can also look at water storage and collection of water from the rooftops. On the left there is the Chesapeake Bay Foundation, where they recycled pickle barrels from an old pickle factory to create these rainwater storage tanks. They're located high in the building, so they actually do gravity flow delivery of water to the toilet fixtures and certain other uses within the building. And on the right is a historic rainwater harvesting system from New Orleans, where rainwater systems used to be very common, almost ubiquitous, apparently. In terms of backup heat, wood energy is what makes sense in a rural area. It's not what makes sense in a good bit of the country. There are air pollution problems with extensive wood combustion, but in times of emergency, you know, in this part of the country, having a wood stove for emergency use makes sense. Pellet stoves are also a possibility, although pellet stoves require electricity to operate. They've got a fan that does a forced air combustion. It's higher efficiency, it's cleaner burning, but it does require electricity. When we bought a pellet stove a few years ago for an apartment above our garage where our business used to be located, we bought a model that has DC fan motors on it, and a kit you can get so that if you lose power, you can clip on basically a little jumper cable and bring in an electric 12-volt battery and run the fans to keep that system operating during a power outage. So from a resilience standpoint, if you want capability during a power outage, that's something to consider. And it's also something I've promoted with fossil fuel heating systems, that the industry in developing furnaces and boilers should be looking at DC components that can be better coupled to either backup generators or daytime use of photovoltaic power. I meant DC motors that'll operate the pumps and fans of those systems. So there are ways that we can make our heating, ventilating equipment more resilient, but it would take some redesign of that equipment. Solar water heating can make sense. This is a system, friends of ours in Guilford, Vermont, that have combined a pretty small solar water heater with a wood stove heat exchanger, so that in the winter months, when the solar is less, The wood stove takes over and thermosiphons passively up to the storage tank, which is on the second floor. Very simple system. Keeps that tank hot in the summer. The single panel is enough to keep that hot. Most solar water heaters in our climate don't provide 100% of the hot water use in the winter. So combining with a wood system, if you use wood for heat regularly, can make sense. And then photovoltaic power provides really the ultimate in resilience from an energy standpoint. Generating your own power for lighting, for operating heating systems, for all uses, water pumps. The problem is 95% of photovoltaic systems that are going in are grid connected. That you have a net meter system plugging into the electric grid, and the vast majority of those systems cannot operate when the grid goes down. I've been pushing the industry for a while to develop lower cost inverters that can operate in dual mode, sometimes referred to as an islanding mode, where if the grid goes down, you would still be able to use power from these inverters for daytime use when the sun is shining, even without battery storage. And there are a few companies that make these, and there are more coming out. I just got an email yesterday or a couple days ago from one of the big inverter manufacturers that's about to introduce such a product, and I look forward to getting the details on that. But it's an important consideration if you're wanting to rely on your photovoltaic system for backup power during outages. This is a system that allows you to do that today. It's this Sunny Island from SMA Americas, one of the big international inverter manufacturers. To operate this, you still need some battery power, a battery bank, but it can be pretty small. You basically need enough voltage from a battery to reestablish the flow of the inverter in the event of loss of grid power. And by the way, the reason this is sort of complex circuitry, with grid-connected photovoltaic systems, the utility company needs to know with full confidence that when the grid goes down, your grid-connected photovoltaic system won't continue pumping electricity into the grid, because there'll be linemen working on those power lines, and the last thing they want is this wayward current coming in from somebody's photovoltaic system. So there are good reasons why this is a challenging installation, but the circuitry can be done, and it is being done, and there are now products available. So this system for a residential sized PV system, a single 100 amp hour battery can provide that use. Now that's not going to be enough battery power to watch your plasma TV all evening on without the grid power, but it will be enough to establish that current flow in the inverter during the daytime when the sun is shining and those PV panels are generating electricity. And the advantage from a resilience standpoint to having electricity, even if it's only during the daytime, is that it will allow us to charge up our refrigerators, freezers, pump water, especially if we have some kind of reservoir, be able to do these key functions, operate our heating systems during the daytime to get the temperature back up, let it drift down at night when the photovoltaic system isn't working. But even without a whole battery system, which is expensive and has a lot of environmental burdens, with a PV system and one of these islandable inverters, we get that level of resilience. Just a photo. The systems can either be roof mounted or ground mounted. This is a Vermont-based company that makes these all-sun trackers, all earth renewables up in the Burlington area. Great company. This is a PV array at Shelburne Farm at one of their big barns. It's a neat installation if you're up there. And I think they've done a real good job integrating that into the backside of this particular barn. Okay, so that's talked about energy. Now I'm going to shift just for a few minutes. What's our time? 4 o'clock. We need to end pretty soon, don't we? Yeah, sorry about that. I wanted to talk for a little bit about communities and community resilience. You know, with looking at creating resilient communities, we want to be able to get around without cars. You know, what happens if gasoline supplies get curtailed for some reason, whether it's pipelines going down or refineries or pricing going up so high that more people simply can't afford gasoline. So there are ways to do that, and you know, Brattleboro's gone through an exercise recently looking at walkable communities. Some of you may recognize this. This is Canal Street heading toward the center of Brattleboro. You know, a classic horrible strip. You know, it's where you take your life in your hands to walk across the street. They did an inventory there of you know, what the opportunities would be for making it more friendly. And this is, next photo is a rendering, shows what that same view could look like with sort of a pedestrian-friendly, smart design. You know, with the buildings brought closer to the street level, parking in back, roundabout that changes the viewscape so you're not encouraged to speed up. You know, traffic calming ideas. Dan Burden, who's with a company called Active Living Workshop. Now, I guess that was the workshop that was done, but he's got a company that consults around the country on more walkable communities. So there are great things that can be done. We can also plan for bicycle commuting, bicycle travel. This was from when I spent a while in Sweden a few years ago. Lund, Sweden has a whole network of bicycle pathways that, you know, have 2-lane bicycle travel with walking sidewalks on the side. I was amazed in Lund to see just how reliant they are on bicycles. I arrived there in December. It was early evening, dark. You know, they're pretty far north. Raining, and everyone was on bicycles still. You know, at the train station, there are, you know, these massive bicycle parking lots. On a middle of a weekend shopping day, when the streets were full of people and bicycles, about the only open space I found in the center of Lund was this parking lot on the left, you know, with a few Volvos and Saabs, but otherwise empty because people simply don't drive. They walk everywhere. So it's really exciting to see that right next door in Copenhagen, Denmark, even greater focus on bicycle travel. So it can be done. The system on the right is kind of neat because the bicycle lane is protected from the traveled lane by the row of parked cars. And then the pedestrian walkway is inboard of that. So there's sort of levels of protection for pedestrians and bicyclists. And then I'll just finish with this slide of integrating food production into the built environment, into our communities. This is in Upper East Side in New York City, a half-acre greenhouse that's built on top of a number of historic buildings. Eli Zabar, who has a grocery system and bakery. There's a bakery right down here. The vinegar factory is a store, but next to it is a bakery where they bake bread and rolls for about 1,000 restaurants in the city. And they take the waste heat from that bakery to heat this greenhouse where they grow tomatoes and herbs that they sell at very high prices in this store right downstairs. So it's a neat opportunity. We also have community gardens and even farming in urban environments. This is just that rooftop Eli Zabar there and one of his associates growing produce on top of this roof. For more information on resilient design, our publication Environmental Building News, we did an in-depth article on it a few months ago, and I did a series of blogs that you can find on our website. Feel free to email me or pick up a card if you like. I can send you information on that. This is our office in Brattleboro. It's 1850s. Barbara George, the owner of it, can tell you exactly the history of it. but it's great to be in a historic building, slate shingle sided, and we love that we're in a building that's being reused in a productive way. So with that, thank you very much, and sorry to keep you a little longer.